With the increasing accuracy and reliability of navigational receivers, this part of the CBT module will try to establish a better understanding of the mathematical definition of the Earth's surface and mapping of this curved shape onto a plane surface. Chart projections constitute the way of representing the Earth's surface in a plane. Distortions are impossible to avoid when representing a surface with double curvature in a plane surface. Different methods for representing this are designed to keep certain properties of the ellipsoidal surface undistorted. The different possibilities are: conform. The charts are angular correct, that is, any angle on the chart is exactly the same on the Earth. For example, Mercator or transverse Mercator projection. Equivalent. The areas on the chart are correct, that is, the ratio between any area on the chart and the corresponding area of the Earth is correct. Charts used at sea for navigation are normally made in Mercator or transverse Mercator projections. On a Mercator chart, a straight line between 2 points represents the course between the points. Chart projections are classified according to the type of projection surface used. The three commonly used surfaces are the plane, the cone, the cylinder. Most navigation charts are constructed using a cylinder projection. The two most commonly used of these are the Mercator and the transverse Mercator. Geodesy is the science concerned with the exact positioning of points on the surface of the Earth. It also involves the study of the exact size and shape of the Earth, the study of variations of the Earth's gravity, and the application of these variations to exact measurements on the Earth. This figure represents a vertical slice through the Earth. It shows the uneven surface of the Earth, but for survey purposes, they are reduced to the geoid. The geoid is a surface along which gravity is always equal, and to which the direction of gravity is always perpendicular. Since the geoid refers to the actual size and shape of the Earth, the uneven distribution of the Earth's mass makes the geoidal surface irregular. Such an irregular surface has serious limitations as a mathematical Earth model because it has no complete mathematical expression. Small variations in surface shape over time introduce small errors in measurement. The irregularity of the surface would necessitate a prohibitive amount of computations. For geoidic mapping and charting purposes, it is necessary to use a regular or geometric shape that closely approximates the shape of the geoid, which has a specific mathematical expression. This shape is called an ellipsoid, which is referred to as a spheroid. Rotating an ellipse about its minor axis forms an ellipsoid. Geodesists use the term flattening, to indicate how much an ellipsoid departs from a spherical shape. For the Earth, this flattening has a ratio of about 1 to 300. Since the surface of the geoid is irregular and the surface of an ellipsoid is regular, many different ellipsoids have been developed to provide a best fit to the geoid for different areas of the Earth's surface. The figure shows two different ellipsoids. One fits well in Europe but not in Africa, and the other fits well in Africa but not in Europe. Before a particular ellipsoid can be used for positional calculations, its relationship to the geoid must be defined, and the definition of such a relationship is known as the datum. The ideal geodetic datum for a worldwide reference system is one that is truly geocentric and oriented through the two poles and the Greenwich meridian. Derived from this are the following two groups of datums. Local datums that are based on convenience and best fit a certain area. Satellite datums that are used for global references. The first satellite datum, established in 1972, was based on the Navy navigation satellite system. This system was also known under the name Transit. In 1989, the NNSS satellite datum was replaced by the Global Positioning System based World Geodetic Survey 84 datum. WGS-84 is a global datum system based on many points fixed with great accuracy. The result is an ellipsoid that is centered on the Earth's center of mass and that fits the geoid far more accurately than any other does. WGS-84 is the reference datum for GPS, and this relationship can be the source of significant error for navigators wishing to plot a GPS fix on a chart that is not referenced to WGS-84. In order to convert positions on one datum to positions on another, it is necessary to establish the relationship between a number of known points that are common to both datums. Most maritime charts contain a source date diagram, or explanatory notes, that provide information on the origin, scale, date, and limits of the hydrodynamic surveys used in compiling the chart. These notes also include information about the origin of the topographical data, the projection used, the datum to which positions on the chart are referred. Some charts will have a note, Satellite Derived Positions. This normally means that if a GPS is used for positioning, positions obtained from the GPS must be adjusted before they are used together with the map. This is a specific example taken from chart BA 2449. Remember that no transformation is perfect, because both the original datum and the datum to which positions are adjusted have inherent weaknesses that vary over their area of coverage. The parameters used within GPS receivers for the transformations from one datum to another are likely to be meaning values for the whole area. Their application, particularly in the extremities of the area, of an inaccurately defined datum, could introduce errors of hundreds of meters. In conventional navigation, that is, plotting ships' position manually onto the chart, it is better to keep the GPS receiver referenced to WGS84 datum and to apply the datum shift values shown on the chart to the WGS84 position output from the receiver. Seen from a navigator's point of view, all charts should have been referenced to WGS84. However, this is not likely to happen for many years. There are several reasons for this. WGS84 is a relatively new datum. Even with sufficient economic backing, it would take a considerable period of time to replace existing charts with new additions using the new datum. Lack of controlled data in some parts of the world. Various political reasons in several countries delay the process. Some charts carry a note indicating the datum shift values for GPS derived positions cannot be determined. These are charts for which insufficient detail is known about the horizontal datum. It is important to note that in worst cases, such as isolated oceanic islands, positions may be several miles different from those derived from GPS. In such cases, mariners are advised to make a greater use of traditional methods of observational position fixing when close to shore or navigating in the vicinity of dangers. The relative positions of features may be more reliable for navigation than the use of unadjusted satellite-derived positions on a chart, whose horizontal datum cannot be defined. This illustration shows the horizontal datum differences in meters that exist between positions referred to OSGB 36, ED 50, WGS 72 and WGS 84 datums in the Dover Strait. Thus, for example, an uncorrected GPS position referred to WGS 84 datum plotted on a chart referenced to OSGB 36 datum would have an error of 139 meters. Satellite navigation has made the art of position fixing extremely easy for everybody. However, position fixing is not the only parameter to take into consideration during a voyage, as long as safe and efficient navigation of a ship remains the goal. The author of this CBT believes that professional and experienced navigators will still be needed on ships for many, many years to come. On the following pages, you will be asked some questions.